Rendering is the computational process that transforms three-dimensional digital models, lighting, textures, and shaders into a flat two-dimensional image or video file that you can view on your screen. It is the final step that creates what you actually see when you watch a game, animation, or any digital visual content. Think of rendering as the process that takes all the invisible three-dimensional data behind the scenes and turns it into pixels you can see. The rendering pipeline consists of three core stages that work together to produce your final image. First, the application stage handles all the scene setup, animations, and data management using the Central Processing Unit, or CPU. Next comes geometry processing, where the graphics processing unit transforms three-dimensional coordinates into two-dimensional screen positions and calculates per vertex lighting. Finally, rasterization converts this geometric data into pixels and applies colors, textures, and final effects to produce the image you see. Rasterization is a rendering technique that converts three-dimensional vector graphics and models into a pixel-based image that displays on screens. It works by projecting three-dimensional triangles onto a two-dimensional surface, determining which pixels are covered, and then applying shading to those pixels. Rasterization is extremely fast because it uses GPU parallel processing, making it perfect for real-time applications like video games where you need 30 to 60 or more frames per second. The GPU processes thousands of pixels simultaneously, which is why this technique dominates interactive graphics. Ray tracing is a different rendering approach that simulates how light actually behaves in the real world. Instead of just drawing pixels, ray tracing traces imaginary light rays from your camera through each pixel into the three-dimensional scene, bouncing them off surfaces to simulate reflections, refractions, and shadows. This produces incredibly photorealistic results with accurate lighting effects. However, ray tracing is much slower than rasterization because it requires many complex calculations per pixel. Traditionally, it was only used for offline rendering in films and visual effects, where quality matters more than speed. Today, with powerful graphics processing units, real-time ray tracing is becoming possible in modern games and applications. There are two main approaches to rendering. Real-time rendering generates images immediately and interactively, typically at 30 to 60 frames per second, and uses rasterization as its primary technique. It is essential for games, virtual reality, and interactive applications where you need instant feedback. Pre-rendered or offline rendering takes hours to days per frame and uses ray tracing or path tracing techniques to achieve photorealistic quality. Offline rendering is used for films, animations, and visual effects where quality is more important than speed. Real-time rendering requires powerful GPUs, while offline rendering can use render farms to distribute the work. Real-time rendering offers good quality with less detail, while pre-rendered graphics achieve photorealistic results. The rendering pipeline has 5 detailed stages. Stage 1 is the application layer where the CPU handles scene setup, animation playback, collision detection, and data management. Stage 2 is vertex processing, where the GPU transforms three-dimensional vertices to two-dimensional screen space, applies vertex shaders, and computes lighting per vertex. Stage 3 is rasterization, which converts geometry to pixel fragments and determines pixel coverage. Stage 4 is fragment processing, where per pixel color is calculated using fragment shaders, texturing, and lighting effects. Finally, Stage 5 is output merging, where depth testing ensures closer objects appear in front, blending combines colors, and the final image is written to the frame buffer for display. The Graphics Processing Unit, or GPU, is the heart of modern rendering. Unlike the Central Processing Unit, which has a few powerful cores, the GPU has thousands of smaller cores that work in parallel. This massive parallelism allows the GPU to process millions of pixels and vertices simultaneously, making rendering dramatically faster than what the CPU alone could achieve. GPU acceleration enables real-time rendering at 30 to 60 frames per second by handling vertex processing, rasterization, and fragment processing all in parallel. The GPU also has high-speed video memory, called VRAM, that stores textures and rendering data locally, reducing latency and improving performance. To achieve smooth rendering performance, developers use several optimization techniques. Scene simplification reduces polygon counts and uses level of detail models, so distant objects use fewer polygons. Texture optimization compresses textures, uses texture atlasing to combine multiple textures into one, and matches texture resolution to the display size. Shader optimization minimizes shader complexity and reduces calculations per pixel using efficient algorithms. Culling and frustum techniques skip rendering objects that are outside the camera view. Occlusion culling further optimizes by not rendering objects that are hidden behind other objects. These techniques maintain visual quality while dramatically improving rendering speed and frame rates. Real-time rendering powers many industries and applications. Video games use it to create interactive three-dimensional worlds with immediate player feedback. Virtual reality relies on real-time rendering to create immersive experiences where movements trigger instant visual updates. Augmented reality overlays digital three-dimensional content onto the real world in real time. Architects use real-time rendering for interactive visualization of building designs before construction. Film and television use real-time rendering for visual effects preview, live compositing, and production acceleration. E-commerce platforms use it for three-dimensional product visualization, allowing customers to interact with and customize products. Training simulations use it for flight simulators, driving simulators, and educational platforms. Automotive companies showcase designs interactively, and industrial designers prototype and iterate on products in real time. The future of rendering is being shaped by several exciting trends. Artificial intelligence and machine learning are being used to optimize rendering automatically, accelerate denoising to reduce noise in rendered images, and enhance scene optimization. Cloud rendering distributes rendering work across cloud infrastructure, enabling global collaboration and massive scalability. Hybrid workflows are merging real-time and pre-rendered techniques to create flexible and efficient production pipelines. Immersive media like augmented reality, virtual reality, and mixed reality demand advanced real-time rendering at massive scale. These technologies are making rendering faster, more efficient, and accessible to more creators and industries than ever before.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.